Edo did his graduate work at Caltech. He followed that up by a postdoc stint, one postdoc that at both Carnegie Observatories and Princeton, so it's Prize Carnegie Princeton Fellowship. He was also a Hubble Fellow at the time. And then he went straight to Harvard University where he was a professor. So Edo is best known for his work on transients. He does a lot of multi-wavelength observations, particularly of GRBs and core-collapsed supernovae, and he's currently involved in pan-stars and other transient surveys. And he's also done some very interesting work on low-mass planets and brown dwarfs. And I think today he's going to talk about some of his work on gamma ray bursts. So,
thank you, Shane. It's a pleasure to be here. And what I wanted to tell you about today is observations of short-duration gamma ray bursts, which until recently were probably the biggest open question in the field in terms of what is actually causing these short-duration events, what are their progenitors, and what are their properties, what's their distance scale, very basic questions that we could not address until a few years ago. And one of the exciting aspects of short GRBs, as I will show you in this talk, is that they've been long suspected to be the result of compact object mergers, neutron-star, neutron-star, neutron-star black hole mergers, which we now have, I think, fairly solid evidence to support. And of course, those are the sources that advanced LIGO is going to go after. And so I will spend the latter part of my talk essentially addressing the question of what can we learn from observations of short GRBs to inform ourselves about electromagnetic follow-up of sources that will be discovered by LIGO in the coming years. Okay, so the objectives of our research in studying short GRBs is, as I mentioned, we want to understand the properties of what until recently was a fairly poorly understood population of gamma ray bursts, and test the association with GRBs, of short GRBs with compact object mergers. And then if we can establish that association, and essentially we've seen at least an on-axis manifestation of compact object mergers, and we can use that information to understand what they look like off-axis, which will be the majority of the cases. So in this talk, I'll just give a very brief overview of what GRBs are, our basic understanding of how they produce energy. And then I'll focus on several points, first demonstrating that the progenitors of short GRBs are distinct from the progenitors of long GRBs, which we understand reasonably well. And then showing you that we now have evidence, partly circumstantial and ready to be a bit more direct, that the progenitors of short GRBs are compact object mergers. And then I will discuss what we can learn about these systems, which in and of themselves are not well understood systems. There are only a handful of neutron-star binaries known in the Milky Way, and there are quite a few more short GRBs, so we can hope to actually learn something about these binary mergers from short GRB observations in terms of distribution of merger timescales and the energy scale of the merger. And finally, I will draw conclusions about what are the implications for as we think about electromagnetic follow-up of sources from advanced LIGO. Okay, so the essential history of GRBs in one slide. So as probably most of you know, GRBs were discovered serendipitously in the late 1960s by the Vela satellites, which were launched to monitor compliance with the Nuclear Test Ban Treaty. And instead of detecting nuclear explosions, they found these bursts of gamma rays that were coming from outside the solar system. And really for the first kind of 20, 25 years in the study of GRBs, as more and more of these events were detected, it was completely unclear where they were coming from, other than the fact that they were not very local. The first advance in this sense came from observations in the 90s from BATSI on the Compton Gamma Ray Observatory, which demonstrated a uniform distribution of GRBs on the sky that was highly suggestive of an extragalactic cosmological origin at large scales. And that was eventually confirmed with the discovery of afterglows at longer wavelengths, at X-rays, optical, and radio, that allowed for pinpointing exact positions for GRBs. So here's an example of an optical image taken a few hours after a GRB, compared to an archival image of the same field taken a few years before. And you can see there's a new source over here that wasn't there previously. This is the optical afterglow. So with a precise position, we can then either measure the redshift directly from the optical light that's coming from the afterglow or from the associated galaxy. And that established the cosmological origin for the long duration GRBs. So this happened in 1997. Now this cosmological distance scale meant that the energy release of GRBs is enormous. The isotropic equivalent energy release is approaches 10 to the 54 ergs. So it requires quite an extreme mechanism to produce it. And the standard model of GRBs has essentially three components. First one is some sort of a progenitor system that can give rise, most likely, to a hyper-accreting black hole. And so the kind of popular ways of doing this is either core collapse of a massive star to a black hole, forming an accretion disk, or the merger of neutron stars in a binary, or a neutron star being tidally disrupted by a black hole. So whatever exactly is happening, and this is one of the big questions, can we understand what the progenitors are? We have this hyper-accreting black hole. It produces some sort of an outflow, either magnetic or baryonic, that has instabilities that lead to gamma ray emission.
Not eternal shocks.
Yeah, some people like eternal shocks, some people don't, and there are lots of arguments about this. But the basic idea is that there is some scale at which energy is being dissipated from the outflow with a very large Lorentz factor, some of 100 and 1,000, maybe even more, and that is the source of the prompt gamma ray emission, highly variable and with a wide range of durations. And then eventually this flow interacts with the environment surrounding the progenitor, and it produces the afterload, which produces light and X-rays visible all the way down to radio. And here's an example of an afterglow. You can see the X-ray emission plummets, the optical emission declines, the radio emission initially tends to rise and then is followed by a decline. Now the other thing you can see in this cartoon is that the outflow is not spherical, it's collimated in a jet. And we now have both evidence that this is indeed the case and measurements of the opening angles of these jets, which we can find from the behavior, the temporal behavior of the afterglow. I'll come back to that later on. So this is essentially the basic picture. And once we correct for beaming, at least for long GRBs, the energy scale is actually very similar to a supernova explosion. It's about 10 to the 51 ergs. The key difference is that the Lorentz factor is 100 or so at early time instead of a typical velocity for supernova explosions of 10,000 kilometers per second, and they're collimated in narrow jets instead of being roughly spherical. So this is a very different beast from a supernova explosion. So the other important piece of information that came from this very large sample of about 3,000 gamma ray bursts from BATSI is that the distribution of durations is bimodal. So this is just a histogram of durations ranging from 10 milliseconds to 1,000 seconds. And so you can see that overall there's a very wide range of durations, but there seem to be two populations that have been termed long GRBs and short GRBs. And the dividing line is somewhere around 1 or 2 seconds. It's not exactly a clean dividing line, but that is roughly where the two populations are separated. And this is what they look like. In many respects, the gamma ray emission from long and short GRBs, if I remove the time axis, it would be very hard, based on other properties, to distinguish a short from a long GRB. Okay? So the duration seems to be the key parameter, although people have been looking for other parameters.
Do you know what the width of the duration corrected long GRB is?
You mean corrected for redshift?
Yeah, I've never seen that. I mean, I'm sure it must have been done.
Yeah, well, so it doesn't shift by a lot because so the typical redshift, for example, for a Swift GRB is about 2. So
But the
we'll
question
shift things
is, does
down by 2.
the tail get contracted significantly?
No. So we've seen GRBs with durations of 1,000 seconds, both at redshift essentially 0 and at redshift 5 or 6, and so this is not determined by time dilation effects.
So did the short bursts have the same big upswings following the initial burst that we see in the long burst?
Yeah, so it's a little bit hard to see in this case, but there is a big spike and then there are additional spikes, so they show a very similar level of variability. Yeah.
Well, the Swift data, as you maybe discussed, has really made it a little bit ambiguous what one means by the duration, of course.
That's right, there's a bit of an ambiguity, but so my operational definition here when I talk about short GRBs is still using this dividing line of 2 seconds, and as I'll show you, there are so many differences when you do this between the short and long GRBs that even though that line might shift a little bit, it's not, it hasn't gone away completely. Okay, so in the Swift sample, which is the sample I'll be talking about, and the BATSI sample of short GRBs is much, much bigger than Swift, but none of them have any redshift measurements or any other auxiliary information. The Swift sample is the one where we have the first detailed measurements of short GRBs, and about 1 out of 10 Swift bursts is a short burst, so about 1 a month.
Can you say something about why the numbers change during short?
That has to do with the fact that the short GRBs tend to have somewhat harder spectra in their prompt emission, and Swift triggers in a softer energy band than BATSI. Okay, so how do we study these GRBs? So we get the alerts from Swift. This is the gamma ray instrument on Swift. They send the alerts down to the ground within about a minute of when a GRB is discovered. I and my students get an alert on our cell phone, and then we rush around and we use a variety of telescopes, both on the ground and in space, to study the afterglow emission, and we have to do it all the way from radio frequencies to X-ray energies. If we want to measure the properties of the afterglow, things like the energy scale, the blast wave, the density of the surrounding medium, the opening angle of the jet, we have to study the afterglow all the way from radio to X-rays because it's synchrotron emission that's very broad. Okay, and so if all we did was study the optical emission, we would not get the full story for these parameters. Okay, so we rush around on a very fast timescale with all these different facilities, and just to kind of give you a sense, here's a recent GRB from June of this year, and just kind of a time sequence from when the discovery was made with SWIFT. You can see that within the first hour, we already had observations going in various facilities. Within 6 hours, we found the afterglow. So here's the afterglow next to the galaxy. A couple of hours later, we already knew the redshift of the galaxy. A few hours after that, we detected the radio emission. We triggered observations with XMM. After about 9 days, there were Hubble observations, and by day 13, we already had a paper on AstroPH. Okay, so things move fast with GRBs in terms of having to do the sequence of observations.
Is it a particularly interesting one, or do you write papers about most of them?
So this is a particularly interesting one. I'll come back to this one a little bit later. We usually, I mean, we've done this before even faster than 13 days, but that requires something that's definitely special, and more competition to some extent is driving us to. Okay, so, but in terms of actually triggering the sequence of observations, that has to happen rapidly. These afterglows, to give you a sense for short GRB, the typical brightness of the optical emission within the first 5 or 6 hours is about magnitude 23. Okay, so we have to act fast and we have to use big telescopes. Okay, so the first thing I want to talk about in terms of short GRBs is their environments and what it can teach us about the progenitors. Why do I care about environments? It's because actually the types of galaxies, the different explosions or transients happening can teach us a lot about what their progenitors are. And not only the type of galaxies, but where they happen within their galaxies. Okay, so here's just an example. Here are 3 types of supernovae, 1A, 1BC, and type 2. And you don't have to know anything about what these are, but you can see that type 1, BC, and type 2 never happen in elliptical galaxies. And they happen much more predominantly in spiral galaxies. Whereas these objects called type 1A supernovae happen with more or less the same rate in all galaxy types. So even if you knew nothing else about these objects, your first inclination just from this fact would be that whatever was causing these objects belonged to some sort of an old stellar population that exists in both spirals and ellipticals, whereas these kind of sources avoid ellipticals, that means they come from a young stellar population. Okay, and indeed we know that type 1 BC and type 2 are core collapse supernovae from massive stars, and type 1As come from thermonuclear explosions of white dwarfs. And they can occur in all types of populations. So the environments are a very powerful tool to tell us something about the progenitors. Okay, so let me start by telling you a little bit about the environments of long GRBs, because I'll use that as a counterpoint for short GRBs. So we know that long GRBs come from the death of massive stars based on various lines of reasoning, and I'll walk you through them. And a lot of it has to do with environments. So first of all, long GRBs happen exclusively in star-forming galaxies. So we've never seen a long GRB in an elliptical galaxy. In fact, not only star-forming galaxies, but highly star-forming galaxies with very young stellar populations, very high star formation rates. So that's already pointing to an association with massive stars. Now, if we look and ask the question, where do they occur within these galaxies? We find, so this is the distance, the cumulative distribution of distance between the position of GRBs and the centers of their galaxies, normalized by the size of the galaxy. So generally what you'd expect is that objects that happen and trace where star formation is happening, half of them will be at about the half-life radius and half of them will be outside the half-life radius. So that's the expected distribution here in a thin line, and these are the data, and you can see that they actually track reasonably well. So not only are long GRBs coming from galaxies that are forming stars, they're also tracking where star formation is happening.
So I guess it peaks a little bit inwards because of that.
Yeah, Now there's another way to look at it, to ask the question a slightly different way. Rather than asking where do they happen in terms of offset from the center, I can ask the following question. Let me take each galaxy and ask and rank the amount of light in different pixels in my image, and ask where did the GRB happen within this ranked distribution? Did it happen in a faint pixel, in a bright pixel, and so on, and make a cumulative distribution. So if objects just traced the light distribution linearly, they would go along this diagonal line. And this is indeed the case for core collapse supernovae. So this red distribution is for core collapse supernovae. They tend to have sometimes in faint places, sometimes in bright regions, but tracking along. Long GRBs, which occur below this line, that means that they're unusually concentrated in the brightest parts of the galaxies. Again, this is relative to the ultraviolet light. So that means that they're coming not just from where star formation is happening, but they're coming from the brightest star-forming regions of their host galaxies. Okay, so this is telling us that they're not just the average run-of-the-mill massive star. They are occurring in special environments that have unusually high star formation rates.
And also they're very massive stars.
And presumably very massive, yeah. Okay, so remember these distributions because I will come back to this when we talk about short GRBs. Now, in the case of long GRBs, we also have another very nice direct line of evidence that they come from core collapse, which is that we see them associated with supernova explosions. So for nearby long GRBs where we have enough sensitivity, after a period of about 10 days from the discovery of the GRB, we see the emergence of light from the supernova that exploded at the same time as the GRB. And there is a delay because the supernova takes longer to become optically thin. But we now have that kind of direct evidence for quite a few long GRBs, and so we know that they're coming from the explosions of massive stars. Okay, so what are our expectations for progenitors of short GRBs? So I should mention before I say that all of this information that I showed you has come from a wide range of observations, starting with the discovery of afterglows of long GRBs in 1997 and until about 2003, 2004, we had kind of a basic picture of the progenitors of long GRBs. The reason I'm posing this as an open question is that we have not seen afterglows from short GRBs until 2005. Okay, so this is a much more recent development. But people have been thinking about potential progenitors for short GRBs for a while, and motivated primarily by the fact that the durations are much shorter, so it's unlikely that they're coming from large, massive stars. They probably need to arise from a much more compact system. And an attractive system is a neutron star binary, undergoing a merger to form a black hole surrounded by an accretion disk that can then drive a relativistic alpha. So what are the expectations for this model that we can now test with observations? Well, the system is born initially after 2 supernova explosions, and depending on the initial separation of the binary, the time from formation to merger can range from a few million years to many Hubble times. And so there's a very broad delay time distribution that's expected in this model, and that means that some of the systems will merge fairly rapidly while the galaxies still have ongoing star formation, whereas some of them will merge after many billions of years when these galaxies have ceased to form stars and will look like living galaxies. So unlike long GRBs, we expect short GRBs in this model to occur in all types of galaxies. And this will also affect the redshift distribution. So imagine a scenario where typically this merger timescale is 10 billion years. Okay, that means that we will not see short GRBs at redshift 1 when the universe was only 7 or 8 billion years old. We'll see them preferentially at very low redshift. So the redshift distribution will also tell us something about the delay time distribution. Another expectation is that these systems, during the formation of the supernova, during the supernova explosions, will receive systemic kicks of potentially tens or hundreds of kilometers per second. And if we couple that with merger timescales of hundreds of millions of years or billions of years, that means that they can travel quite a large distance from the birth site of the binary before they merge and produce a short GRB. So we expect that some of these could travel maybe 100 kiloparsecs away from the galaxy at the time that they will merge. So they will have large offsets from the galaxies, and they will explode in relatively low density environments, not in the interstellar medium of their galaxies. We also expect R-process nucleosynthesis. We have this ejected material that's neutron rich and can lead to R-process nucleosynthesis. Until recently, I would say that's a prediction that maybe we will see one day. But I'll show you towards the end of the talk that I think we now finally have seen that process in a short GRB. And finally, of course, gravitational waves, which hopefully we will see in the next few years. Now, there are other models, giant flares for magnetars, and Chris is here. So you probably all know about magnetars, but the idea is that we see short GRB-like episodes from magnetars, the soft gamma ray repeaters. And so if some of these outbursts are very energetic and the recurrence timescale is very long, they might masquerade as short GRBs. Magnetars are young neutron stars, so we expect to find these in young star-forming environments, probably relatively nearby, and we do not expect them to have large offsets. Even though magnetars can have kicks, the time scale for an object to be a magnetar is relatively short, so they're not going to travel a large distance. Okay, so let's look at some of the observations we've been gathering over the last few years as they relate to these predictions. Okay, so the first thing is that we quite quickly realized and were able to show that at least some short GRBs happen in elliptical galaxies, which is very different from long GRBs. Remember, in over 2 decades of observations of long GRBs, we've never seen one in an elliptical galaxy. And here are 3 examples of short GRBs. So the localization region is the circle over here, and the small circle over here, and this circle over here. And you can see that they occur in elliptical galaxies ranging from a redshift of about 0.2 to about 1. Okay, so this is telling us that at least some of these short GRBs are coming from an old population of stars. They're not coming from young massive stars. In fact, the ages of the stellar populations in these galaxies are at least 1 billion years old. There have been no recent star formation. Okay, so that's already, right away, we know that they're not massive stars, or at least some of them are not massive stars. Now, for some of these short GRBs that are relatively nearby, we have also gone out and searched for an associated supernova, just like we do with long GRBs. So here are a couple of examples. So far, we haven't seen a supernova associated with a short GRB. So here are examples of what even a dim supernova would look like. And here are the observed limits, so well below the expectation. Here's another short GRB with different supernova models, and here are the limits, again, well below these expectations. And here's a sample where I've compared the brightness of supernovae associated with long GRBs, which you can see span quite a narrow range. All of them are within about 20 or 30% of each other in terms of brightness. Yeah, these are the light curve bumps that we see in long GRBs. And then here are limits for short GRBs. And you can see that they're well below the typical GRBs that accompany, typical supernovae that accompany long GRBs. So this is telling us again that the progenitors of these systems are not massive stars. Now what's interesting here is that all of these limits are for short GRBs that happened in star-forming galaxies. Okay, so even though they happen in star-forming galaxies, the progenitors themselves are not massive stars.
Would you get a lower limit? Does the presence of star formation affect your ability to get a limit on that?
I mean, these are at the same redshifts where we see the GRBs that are associated with the supernovae associated with long GRBs quite easily. So. Okay, so I mentioned that the redshift distribution can tell us something about the ages. So just let me show you, so these are just a few examples of spectra of short GRB host galaxies. And the first thing you can see from this, which I should have already mentioned, is that short GRBs are also cosmological in origin, just like the long GRBs. They're not coming from the Milky Way. And we found them out to about redshift of 1 or 1.5. Long GRBs, on the other hand, we've been able to find out to redshift 9.5. And the reason is that there are significantly more luminous objects in the short GRBs. You can see them much further out. So I mentioned that we can use this, the redshift distribution, as essentially a chronometer of the age of these systems. So here's the basic idea. So imagine that we form these binaries at the same time, as massive stars are being formed. So tracking the cosmic star formation history, the peaks at around redshift of 3 or 4. And then we impose some delay distribution. Okay, so for example, the blue curve is for a typical delay of 6 billion years with some spread. And you can see that most of the resulting GRBs will happen at low redshift, about 0.4, because it takes 6 billion years from when the system formed to when it merged. Whereas if the delay is, for example, 3 billion years, as in this green curve, the redshifts will be high. Okay, so we can compare our observations to this. So here's our rough redshift distribution. We have measurements extending out to about redshift 1, and then we have several systems where we don't have redshifts, but we have lower limits that suggest to us, based on the properties of the galaxies, that they're likely at redshifts greater than 1. So we're clearly not sitting in this regime where the progenitors are generally very old. Okay? So it's telling us that if they're neutron star binaries, the typical merger time scale is less than about 3 billion years. Okay? Not all of them are merging within this time scale, but that's kind of a typical number. And we can look at this question in another way. Imagine that you have if the progenitor merger timescales are large, greater than a gigayear typically, that means that the only thing that controls the rate of formation of short GRBs is the stellar mass of the galaxy. Because star formation is already cyst in these galaxies, and so the more mass they have, the more short GRBs they're going to produce. Okay, does that make sense? Okay, so the prediction then is that roughly roughly half of short GRBs will happen in elliptical galaxies, and roughly half of them will happen in spiral galaxies, because roughly half of the stellar mass in the universe is in ellipticals and half is in spirals. So we can actually go and ask the question, what is the distribution of galaxy types? And we find that ellipticals only account for about 15% of the population, okay? Where star-forming galaxies are much more dominant. Now, there are a couple of other populations. One are things like this, where we can't really tell if it's an elliptical or a spiral, or it's too faint, too kind of small, and it's hard to tell. So those are in the question mark. And then we have these hostless events that I'll come back to in a few minutes. These are events where we go and we look, and there is no galaxy. Okay? So those are interesting in their own right. But generally speaking, the ellipticals are definitely not half of the sample. So what this is telling us, essentially, is that star formation actually does play a role in elevating the rate of short GRBs. And that means that some of the delays are actually relatively short. Maybe they're only 100 million years or 200 million years. So galaxies with ongoing star formation are overproducing these progenitor systems. There's another way to look at this, which is the actual masses of these galaxies. Okay? So if mass is the only important parameter, then I can take the mass function of galaxies, which is well known, and I can draw from the mass function a distribution of galaxies that's weighted by mass, and make a prediction for what the mass distribution of short GRB host galaxies should be in that scenario. So that's what I've done here. So here, the magenta curve is the prediction for what the mass distribution of elliptical host galaxies should look like if mass was the only parameter. And here's the actual mass distribution of elliptical host galaxies, and you can see it matches very nicely. If we do this for star-forming galaxies, we get this cyan curve over here. But these are the actual mass measurements for the short GRB host galaxies. So they're systematically less massive than expected if mass was the only important parameter. So essentially, another way to say this is per unit stellar mass, star-forming galaxies are forming 3 times as many short GRB progenitors as elliptical galaxies. And the reason is that they have ongoing star formation activity. They're replenishing the progenitor population. So if they're neutron star binaries, it means that some of these mergers are occurring on a timescale of only a few hundred million years, not many gigayears. Okay. The reason we care about this is already giving us some idea or some way of tracking the range of merger timescales, which we don't really know very well from observations of neutron star binaries in the Milky Way. So what are these numbers? What are the typical numbers? We can look at the ages of the stellar populations in these galaxies, and we find that a typical age of the stellar population in a star-forming host galaxy is about 300 million years, and in an elliptical galaxy it's about 3 gigayear. And when we combine that with the fact that the rate is higher by a factor of 3 in these galaxies than in these, we find that roughly the delay time distribution, the probability of a merger as a function of the time scale, goes like tau to the -1, which is what we expect from kind of naive theoretical calculations for neutron star binary mergers. So I'm not saying that this is evidence that they're neutron star binaries, I'm just saying that the population of progenitors has this kind of a delay time distribution. And that's very similar to type 1a supernova progenitors. They also seem to follow a power law at 12 tau per mile as well. Okay, so there are more mergers happening at shorter delays than at longer delays. Okay, so let me stop here with a few kind of intermediate conclusions. So one, the fact that some short GRBs are in ellipticals and that they are not associated with supernovae is telling us that their progenitors are not massive stars, unlike long GRBs. The fact that the hosts of short GRBs are distinct from those of long GRBs suggests that, again, that they're not massive stars. And from the distribution of galaxy types and the stellar masses of these galaxies and the population ages, we can tell that the rate depends on both mass and star formation and roughly follow tau to the -1. So that's on a galaxy scale. What if we now ask the question, where are short GRBs located within their galaxies? Remember that long GRBs were located near or in spatial coincidence with very bright star-forming regions. What about short GRBs? So to answer this question, we need high-resolution images from Hubble, and we've now collected a sample of about 30 or so short GRBs with Hubble observations. So here I'm showing a few cases. So in each case, the circle marks the position of the GRB, and the size of the circle is about 10 sigma. Okay, so we can locate these positions very precisely. And you can already see just from these images that some of these are happening quite far out from their galaxies. They're not happening where most of the light of the galaxy is located. Okay, but we need to quantify this. Now I mentioned these short GRBs where we have a very precise precise position, and we go with Hubble, and we don't see a galaxy. So these are the objects that we've called hostless GRBs, and those are very interesting. So here are two examples. So here's the position of the afterglow marked by the crosshairs, and you can clearly see there's just absolutely nothing there. Okay, these are very deep Hubble images. And the only way we can hide a galaxy here that is similar to the other host galaxies of short GRBs is if we push these galaxies to about redshift 3 or 4 or beyond. So that is significantly higher redshifts than the population we see, and that's an unlikely solution. So one possibility is that these GRBs came from one of these nearby galaxies. Okay, and it traveled from the galaxy to this location, which would be a signature of these kicks that I mentioned that we expect in neutron star binaries. Okay, so how can we assess this, this potential? Well, what we can do is we can ask, what is the probability that we find these different galaxies there by chance coincidence? I mean, if I take every image from Hubble and put some random location, I'll find galaxies nearby, but I need to assess the probability that they're there by chance. And if the probability that they're there by chance is high, then I cannot claim that they must have come from this galaxy. Okay, so how do we do this? We take one of these images and we just go out from the position of the afterglow, and every time we encounter a galaxy, we ask what's the probability of finding a galaxy of that brightness within a circle of this area. Now, of course, there are a lot more faint galaxies than there are bright galaxies, right? So finding a faint galaxy very far away from that position is not surprising, but finding a very bright galaxy might be. Okay, so the probability is just the product of the area that we're searching and the number density of galaxies. You know, how many galaxies of that brightness per square degree on the sky. Okay, very simple calculation. So if I now do this for the fields where I have these hostless GRBs and plot this probability, I find that generally as I march out from that position, I find galaxies, but the probability of those galaxies being there by chance is 10, 20, 30%, not surprising. I go to very large separation, same deal. But then at a scale of a few to maybe 20 arc seconds, I find this very low probability set of galaxies, you know, 10 to the minus 3, 10 to the minus 4, that should not be there by coincidence. Okay. Now you can say, well, maybe this has nothing to do with short GRBs, maybe this is something about galaxies. They like to be distributed in some way. So we can repeat the same exercise for short GRBs that do have coincident galaxies. Okay, so that's shown in blue. So here are the coincident galaxies at a very small separation, 1 arc second or less. And then we do the same exercise and we never find anything of significance at this kind of separation. So what this is telling us is that those fields where we have identified these hostless short GRBs, there are systematically galaxies that should not be there by chance at separations of about 10 arc seconds.
Which corresponds to...
Which now we can go and measure the redshift. So these are galaxies like this one in this case. And the redshifts are somewhere between about 1/10 and 1/2 typical of short GRB redshifts. And those separations become something like 10s to 100 kiloparsecs.
So they could be, can you rule out satellite galaxies?
To the extent that they're significantly less massive, you know, you can see the contrast, right, between the non-detection here. So if they're satellite galaxies, they would have to be substantially different. Now, they could be globular clusters. That's a possibility, but globular cluster origin would also point to neutron star binaries anyway.
What luminosity limit typically can you set?
Generally around -10 or something like that. So you can hide globular clusters. In any case, you know, these kind of separations, the fact that a short GRB came from this galaxy and the same in the other fields means that, you know, these systems did not, like they formed here. They formed over here and they have to travel from here.
Well, that seems puzzling though. I mean, you could have two different populations with much different kicks.
Sure, sure. But let me show you in a second the full distribution. Okay, so you know, in my mind, this is kind of one of the nicest pieces of evidence that we have that's supporting the compact object merger scenario, because none of the other progenitors that have been suggested are capable of traveling these distances. Okay, so now we can take the full distribution of all the offsets, all the way from the ones that have coincident galaxies to these hostless ones, and I get this red curve. So it extends from about 1 kiloparsec for the smallest separation and down to about 100 kiloparsecs for the largest ones. And I can compare it to other types of explosions. So here are long GRBs, they have much smaller offsets. Here are core collapse supernovae and type 1a supernovae. None of those show a tail that extends to such large offsets. And here are model predictions from neutron star binary population synthesis models, where they've taken large populations of binaries and gave them a distribution of kicks and a distribution of merger timescales and predicted where they should merge. And you can see that the agreement is actually quite remarkable, given that these models have existed in the literature well before the data were obtained. So I think this very nice agreement with the models, I think this is giving us one of the best clues that we are looking at neutron star binaries. Okay, let me skip. Now, I mentioned that there's another way to look at it, which is to ask what is the spatial correlation between any type of explosion and the life of the galaxy. So now this diagram, which was confusing to begin with, now has many more lines. So let me kind of go through this kind of in broad levels. So any type of object that was strongly correlated with light would be in this part of the diagram. Okay, whether it's I compare it to ultraviolet for long GRBs or optical light or whatever it is, it will be in this part of the diagram. Okay. Now, anything that's on the other hand in this part of the diagram is weakly correlated. Okay, so that means that there is no good spatial correlation between where my object of interest is happening and where the light of the galaxy is. So let's take a look at the blue curve, which is the relation between short GRBs and ultraviolet light of their host galaxies. And what you can see is that somewhere between 60 and 70% of short GRBs are happening where there is zero ultraviolet light. Okay, so what this is telling us is that ultraviolet light, which traces star formation, and short GRBs know nothing about each other. They're not happening in the same environments. Okay. Now you can say, okay, well, I've already told you that the progenitors of short GRBs are not massive stars, so it's not surprising. But what if I compare to optical light instead of ultraviolet? Optical light traces just the bulk of the stellar population, the old stars and the new stars, the stellar mass of the galaxy. And so that's the red curve over here. And what you can see that's remarkable is that even when I compare it to just the bulk light of all the old stars, again, about 40 to 50% of short GRBs are occurring where there is no stellar light in their galaxies. Okay, there are no stars there. So what does this mean? There's no way that these systems could have been born where we observe them as short GRBs, because there are no stars there. There are no other stars. So these progenitor systems have no business being in these kind of environments. This is essentially, again, evidence for the same process of kicks. So these systems formed elsewhere in the galaxy where the bulk of the stellar mass is located, but by the time they exploded and produced short GRBs, they have traveled away from those environments to areas of the galaxy where there are no stars. Okay? And that's really the only way to explain how they're completely decoupled from where the stars in the galaxy are located.
Certainly, I completely agree with the conclusion. It's surprising that the 1A's don't correlate better with optical light, isn't it? Or
Well, so you can do a KS test here, and actually, you
it's
know,
also bad.
it's something like the KS p-value is something like 0.2 or 0.3 that they linearly track stellar light. Yeah. Whereas for the short GRBs, it's below 1%.
It's obvious that
Yeah.
that one's clear.
Yeah. So they're happening in environments where there's essentially no stellar mass, and really the only way we can think about doing this is, you know, you can see this in the images. It's very clear. Here's the stellar light from the galaxy, and here's the short GRB. You know, here's another example. This is where the stars are, and this is where the short GRB is. They're not in the same places. Okay, so this is really evidence that the progenitors have to travel from the birth side to the explosion side. And again, really the only model that we have right now in the books that can do this is neutron star binaries or neutron star black hole binaries. So this is why I was saying at the beginning that the environments are such a powerful clue about the nature of the progenitors. I think that with these kind of investigations, we've now shown that that is really the only kind of viable model that we have. Okay, so let me switch gears and talk a little bit about the afterglows. So we've seen afterglows from short GRBs. That's how we localize them precisely. And here are a couple of examples where we've been able to measure the afterglow all the way from radio through optical and X-rays. And that allows us to measure properties like the energy of the explosion and the density of the medium, and in some cases, the opening angle of the jet. And the bottom line is that the afterglow physics, the evolution of the afterglow, the nature of the synchrotron emission is identical to the one in long GRBs. But the energy scale seems to be lower systematically, and the densities also seem to be lower. Now, these are densities on the scale of about a parsec around the progenitor system, so very close to the progenitor environment. And it's telling us something about what kind of environments these explosions are taking place in.
Do those densities seem low enough considering how far away from the galaxies you are?
Yeah, I mean, you know, 2 times 10 minus 3, that's kind of halo.
But the
density.
other ones.
Yeah, no, that's fine. Yeah. Okay, so these are just a couple of cases. We can look at the population as a whole. So what I'm showing here is the optical luminosity of the afterglow as a function of the gamma ray energy. Okay? And the optical luminosity is proportional both to the energy of the explosion, but also to the density of the environment. Okay, so what can we see here? First, we can see clearly that the energy scale of short GRBs, which are shown in blue, is lower than the energy scale of long GRBs, which are shown in red. Right? There's a clear offset from here to here by about 2 orders of magnitude. But we also see that while there is a clear correlation between the optical luminosity and the gamma ray energy, what comes from this, right? The luminosity should track the energy. There's a systematic offset in this direction, which is also telling us that the density scale is lower. So that's the density to the 1/2 component is shifting this whole correlation down. And shifting it down by an amount that indicates that the densities are somewhere between 10 and 100 times lower than for long GRBs. And that makes sense because long GRBs are exploding in these dense star-forming environments, whereas these short GRBs are occurring on the outskirts of galaxies where the interstellar medium density is very low. Okay, so that's kind of a statistical statement for the whole sample. Now the other important part is the beaming, right? The geometry of the explosion. And the reason is that an explosion that's beamed in a jet has a lower energy scale than if we assume that it's spherical. And it also means that the rate of occurrence of those events is proportionally higher by the same inverse factor. Okay, so if the typical opening angle is 5 degrees or so, that means I only see 1 out of 100 explosions that happens to be on the axis, and the energy scale is about 100 times lower. So how do we search for evidence for this beaming? What we look for is characteristic breaks in the evolution of the light curve. Okay, so you can see here an example of an X-ray light curve. It decays with one slope in a uniform way, and then after about a day, that suddenly steepens to a steeper decline. And that is a characteristic that comes from the fact that we see the edge of the jet. And so if there is a jet, there is an edge, and there is missing emission, essentially, compared to something that is spherical. Okay, I can go into that in more detail later. But the key thing is that the timing of the break tells us about the opening angle of the jet. The earlier the break occurs, the narrower the jet is. So we can read off the opening angle from the timing of the break. And then we can have this blue histogram, which shows our measurements so far for short GRBs. And you can see that there are only a few. But they seem to range from something like 5 degrees to some of these where we have a lower limit telling us that it's wider than 10 or 15 or 20 degrees. Now in red are the measurements for long GRBs. There you can see we have a lot more information. The typical angle is about 5 degrees.
What are the arrows?
These arrows are limits. So the reason we have lower limits is imagine if I observed the source and then it dropped below my sensitivity and I never saw a break. That tells us that the break occurred at least later than my last measurement. So that places a lower limit on the opening angle. Okay, so some of these lower limits are not very interesting. They're 2 degrees or something like that. That's not interesting given that our typical detections are at the 5 to 10 degree level. And it's hard to do statistics with this sample, but roughly it seems that the typical opening angle is something like 10 degrees for a short GRB. So that means that the correction for beaming is something like a factor of 30 to 100, which gives us a typical energy scale of only 10 to the 49 ergs. So this is about a factor of 100 less than the energy scale of a long GRB. Remember I said it's about 10 to the 51 ergs. So the energy that's coming out in the relativistic outflows from these binary mergers is much, much less than for a long GRB. Now, it has the reverse impact on the rate. So the observed rate of short GRB is about 10 per gigaparsec cube per year. But now we have to correct it upward by a factor of 20, 30, 50, 100. And then we can ask the question, well, if we think that they're neutron star binaries, how many of these are going to occur within the volume that advanced LIGO is sensitive to? And based on this rate and this correction factor, we find something in the range of about 10 to 50 events per year within the LIGO range. Okay? And that's reassuring. That's the number that the LIGO people like to quote anyway, about 40 per year, of course with a plus or minus factor of 10 uncertainty. But this is a completely independent way of assessing that number, assuming that you buy the story that I hopefully convince you that they are really neutron star binary mergers. Okay? But this is something that will be testable. If advanced LIGO doesn't see of that order of events, then something in the story is wrong. Either our beaming correction is too optimistic, or they're not neutron star binaries. Okay, so that leads me to the last part of the talk, the last few minutes, where I want to talk about how we can now use this information about the afterglows of short GRBs to predict what the electromagnetic counterparts of LIGO sources will look like. And the reason we actually want to find electromagnetic counterparts of LIGO sources is there are several of them. One is that this will allow us to measure the distance scale. LIGO sources will be localized very poorly on the sky, and there will be no way to associate them uniquely with galaxies. But if we can find an electromagnetic counterpart and localize it precisely, just like with GRBs, we can measure the energy scale. The distance scale, that will tell us something about energetics. It's important to know how far away these sources are. It will also give us the astrophysical context. Just like I showed you with short GRBs, once we have very precise positions, we can start asking questions like, where are these events happening in their galaxies? Are they happening in the same place as short GRBs? Are they correlated with star formation, not correlated with star formation? These are very interesting questions for understanding the formation of these compact object binaries. And then finally, the LIGO action will be over once the merger is over. But from the point of view of what happens afterwards, do we form jets from these mergers? Is there ejected material? All of this action will be manifested in electromagnetic radiation, not in gravitational waves. And so we need to find the counterparts to study this.
So basically, you're predicting one gravity wave EM coincidence per year.
Roughly, I'll come back to that in a second. Yeah. Okay, so there are different kinds of electromagnetic counterparts we can think of. One is a short GRB, but that requires us to be oriented along the line of sight with a jet. So that will happen some small fraction of the time. If we're observing the system away from the axis of the jet, we will not see the gamma ray emission, but we could still see the optical emission or radio emission as the jet decelerates and expands into our line of sight. Okay, so even off axis, we can see an afterglow. But there are other possibilities. There is, remember I talked about this R process nucleosynthesis that happens in the outflows from the binary merger. And that R process nucleosynthesis will give rise to radioactive elements that will then decay and provide a heat source that will produce optical or infrared light that we can actually observe. So it will be, and this should be roughly isotropic, so we should be able to see this from any angle. Yeah, but the question is, we can have all these possibilities, but what is actually detectable? And the challenge is that the positions that LIGO will provide, at least in the first few years, are enormous in the sky. They're of order 100 square degrees. Okay, so if LIGO tells us, well, go search this 100 square degrees, and I'm going to look for one of these counterparts, it better be bright enough that I can see it in such a big area of the sky. So let's look through a couple of possibilities for these counterparts. The first is gamma rays. That would be the most fantastic thing because it's such an obvious counterpart, right? So one thing I can already tell you is that we have never seen a short GRB in 8 years of observations within the LIGO volume. Okay, so we already know that the rate is low. But we can extrapolate down to that redshift and then correct for the fact that Swift only sees about 10 or 15% of the sky at any given time. So if we had an all-sky mission, we would see something like one coincident short GRB LIGO trigger every 2 years or so. Just the number that Chris was quoting. And that comes back to my beaming correction number. Okay, so once every 2 years, 1 out of 50, 1 out of 100. That would be fantastic to see that, but this is not the kind of counterpart that we will see on a case-by-case basis. What about the afterglow? Well, on axis, the optical afterglows are very bright. We can see them at redshift 1, so we can definitely see them at 200 megaparsecs. But again, that will only happen once out of 50 or 100 times. But we can see these afterglows off axis. Now, how do we know what they're going to look like off axis? Well, we've seen them on axis, so we can just shift our line of sight off axis and ask, what would they look like? And so here are the measurements of short GRB afterglows, and you can see that they're bracketed by models. So these lines are models for different energy and density scales. And so they're bracketed by these green and yellow lines. So now let me take those lines and pretend that I'm looking from an angle that's twice the opening angle away from the axis of the jet. And those curves become these curves. And the reason there is a delay and an initial rise is this is the time scale for the jet to expand and come into our line of sight. Okay, so these green and yellow lines that bracketed our short GRB observations become these green and yellow lines. And now you can see that the peak time scale is somewhere between 1 and 10 days. So there's a delay of about 1 and 10 days. But the brightness correspondingly goes down. And so now we're talking about sources that are somewhere between 23rd and 25th magnitude. Now, the dotted lines here are the sensitivity limits of existing wide field telescopes, and then LSST, which will come online soon. And you can see that things like the Palomar transient factory or pan-stars, which exist now, are just not capable of imaging such a big area quickly enough and deep enough to see these kind of curves. LSST will be able to do it, but that's 8 or 10 years from now. Okay, now this is when I go twice away from twice the opening angle away from the jet. If I go anything beyond that, this emission becomes so weak that we will never be able to see. So I can ask what fraction of events occur within twice the opening angle, correcting for some other effects. It's about 10%. So maybe twice per year, we might be able to find an optical afterglow off-axis associated with a LIGO trigger, but it's not going to be, again, the case for the bulk of these events. Okay, what about this kilonova? So kilonova is a name that's been given to the emission that will be produced by this R-process radioactive element. And it's because it was predicted initially to be about 1,000 times brighter than a nova. So kilonova seems like a reasonable name. Okay, so the idea is that there is ejection of material that's neutron-rich. It will lead to R-process nucleosynthesis and heavy elements. And the typical scales that people have been finding in simulations is that the outflow velocities are about 10 to 30% the speed of light, and the amount of ejected material is somewhere between 10 to the minus 2, maybe up to 10% of the solar mass. So with these numbers, essentially we can predict roughly how bright these sources are going to be and what their typical time scale is going to be. And the initial predictions were something like a time scale of a day and a luminosity of 10 to 40 watt per second. That's about 100 times less luminous than a supernova. Okay, so these things are going to be fast and dim version of a supernova. Not easy to find in 100 square degrees. Now, one thing that a paper, or a series of papers that came out in the last 6 months changed the story a little bit in the sense that the initial prediction said, well, we don't know what the opacities of these R-process elements is going to be. Let's assume that they're just like iron peak elements. So people have then gone out and actually calculated what, or at least for some of these elements, what the opacities are. And the basic finding is that the opacities are about 100 times larger than for iron peak elements. So instead of getting something where the peak of the spectrum is in the optical at about 5,000 angstroms, the opacities are so large that the peak of the spectrum shifts into the infrared, and there is very little optical light that's actually coming through. So what this means, the opacities are larger, the spectrum will peak in the infrared, the time scale will get smeared out by the same effect, and the luminosity will be even lower. So now we have something that lasts a little bit longer, maybe a week instead of a day, but it produces mainly infrared light, and it's even dimmer. So the question is, can we see this? Well, we had actually a chance recently to do this kind of a search in association with a short GRB, not with a LIGO trigger, but with a short GRB. So this is the GRB that I talked about. I showed you a nice sequence of events, and that we had this paper within 2 weeks. I'll show you what the reason was for that fast paper. Okay, so here's an image of the GRB 10 hours after the event was discovered from the ground. And here's another image in the optical a month later. And you can see here's the galaxy and here's the afterglow. It faded away. And then about a week later, there are HST observations, Hubble observations, in both the optical and infrared. And in the optical, you can see an image obtained, as I said, about a week after, and this is a month later, a week after, a month later. If we compare those two images, if we subtract them, you can see that there's no optical light that's coming through, but there's an infrared source at that position, the same position of the afterglow. Now you can say, well, okay, what's the big deal? This is the infrared afterglow. This was the optical afterglow, it faded away, here's the infrared light. Well, we can compare, we know how the afterglow evolves as a function of time, we can compare those two. And so this is what we see here. So here's, as a function of time, the evolution of the afterglow. And you can see that initially it decays with this slope, and then it steepens, and then it follows this dotted line. And this is what the afterglow will do in the infrared. It will follow this dotted line. And here's our measurement. So it's about 50 times brighter than it should be, than the afterglow should be at that time. Okay. All right, so there's some excess of infrared emission about a week after the GRB, and that should sound familiar based on what I was just talking about. So here are these kilonova models in the infrared and in the optical. Okay, and just like I said, in the optical, the emission dies off extremely rapidly. It's very dim, whereas in the infrared, it has a time scale of about a week. Okay, and the two models are for 10% of the solar mass in ejecta and 1% of the solar mass. So what we see, this excess emission is consistent with this idea of what a kilonova should look like. The fact that we see only infrared light, no optical light, and the fact that we see this excess about a week after, it smells a lot like a kilonova. And the mass of ejecta that we can infer from the brightness is about 0.05 solar masses. Okay, now this is really interesting. Okay, one, this is, if you accept the story I just told you, and we've searched for a lot of other possibilities for what could be producing this infrared excess, and we couldn't find anything else. This is really the most direct evidence we have for neutron star binary mergers being the progenitors of short GRBs, right? The production of this R process rich ejecta. Secondly, it means that although these things are going to be dim in the optical, in the red optical bands, in I and Z band, based on if this is a typical mass scale, the typical brightness of 200 megaparsecs will be something like magnitude 22 or 23, which is something we can actually detect with existing telescopes if we search 100 square degrees. So that's reassuring. And finally, this is typically the amount of R process ejecta from a neutron star binary merger, and we multiply this by the rate of neutron star binaries, which I told you we know to maybe a factor of 100, so it's not a well-known quantity. But if we take the typical rate, then it's telling us that these neutron star binary mergers are actually dominating R process nucleosynthesis. That this is really where R process nucleosynthesis happens. That's been discussed for a long time in the literature. It's not a new idea, but I think this is the first time where we actually have some observations that show this. So when we submitted this paper, we had a press release that talked about R process nucleosynthesis, and we mentioned that one of the things that R process element is gold. And we estimated how much gold is produced in this process, and we found that it's something like $10 octillion worth of gold in today's market rate. So that's where gold comes from. If you ever wondered where it comes from. Okay, let me skip this because I think I'm running over. So that's essentially what I wanted to say. Just to summarize. From studying the environments of short GRBs, I think we now have fairly strong evidence that, one, they're definitely not coming from the same progenitors as long GRBs. They're not coming from massive stars. The fact that we see large offsets, that we see no spatial correlations with stellar massive star formation, and that they have low densities in their nearby environment suggests that they're neutron star binaries. We have evidence for beaming that tells us something about the rate. And we now, I think, have some evidence and some hope that we can actually see the optical or infrared light from this kilonova emission, even if we have to search 100 square degrees. We can actually do this. It's a doable problem if the mass scale that we inferred for the one event is typical. So that gives me a lot of hope that in the next 5 or 10 years, as LIGO starts finding gravitational wave sources, we will be there with our optical telescopes finding their counterparts. All right, I'll stop there.
So on this ejection mass, if I remember the simulations to take them at some face value, I think such really high ejecta masses you only get in black hole neutron star mergers. Is that wrong? I think more equal mass neutron star, nobody finds such a high ejecta mass.
Yes, I agree. Although I would not use that to say that this was a neutron star black hole.
No.
But yeah, no, you're right.
The follow-up was there anything else that was unusual about this burst? It seems mostly unusual that you had the right data, but
yeah, no, there's nothing about the burst otherwise that looks particularly unusual. But I agree that the simulations that people have done.
Timescale on the long or on the short side?
Of the burst itself? It was about 0.2 seconds, so right in the middle of the distribution. The galaxy is not unusual anyway. The distance from the galaxy is not unusual when we compare it to the overall distribution of offset. So right now we haven't seen anything else unusual.
Geometrically, how close was this to the nearest star formation? I mean, it looked like it was just at the edge of the galaxy.
Yeah, so you can see that from the image that the galaxy is quite a disturbed morphology, so it's hard to exactly say where the center of the galaxy is, but the distance is something like 5 to 10 kiloparsecs. But you're asking relative to the nearest star forming.
The nearest light, yeah.
Not very close. So actually, this event is in that distribution that I showed. So I can't remember exactly where it is along the distribution, but it wasn't particularly well correlated with ultraviolet or anything like that. Now, the fact that we have these very deep limits in the optical at around a time scale of a week to 10 days also rules out a normal supernova associated with it. So we know, again, it's not a massive star system. So this is really the first time that we've done the right set of observations. I think we can now do this again, given that we know what we're looking for.
Well, I guess you expect to have multiple components of the alpha. There's the relativistic jet that you were extracting, right? The acceleration of the
So that's a good point. So we've actually
that's
looked at
about
it.
maybe 1,000 for the solar, yeah.
So we looked at the possibility that what if this infrared light is actually caused by some, not the jet itself, but some other outflow component that has nothing to do with this our process of photosynthesis.
Synchrotron.
Yeah, and it's synchrotron emission. So we have radio observations at the same time.
Yeah.
Okay, and those radio observations show they track the optical emission, and they don't show if there was an enhancement in the energy from a mildly relativistic component, it would in fact show up most prominently in the radio rather than in the infrared. So the infrared would just be the tail, and we can predict how much radio emission should be coming out, and we don't see anything anywhere near that. So that's not the, so this has to be an emission component that's really,
Wait a minute, one has to think about self-absorption, the relative importance of self-absorption.
the densities are so low that self-absorption is going to be at,
Times 12.
100 megahertz or something. And we're observing at 10 gigahertz, so self-absorption is not going to be an issue. Yeah, so I think that was our first inclination, is to say, okay, this is not this more exotic explanation, let's look at other possibilities. And one of those was a slower ejecta component that doesn't produce a lot of optical light, produces infrared, but it would be dominated by radio. There's no way of getting around that, and our radio data just ruled that out completely. So it has to be something that's producing preferentially